What's up, everybody? It's Dan from Sage Math Tutoring, and here with a video that pertains to radicals and some trigonometry concepts for a student of mine who has a quiz coming up, and figured I'd go over a few problems. So the directions here are to simplify this, and when being asked to simplify a product of radicals like this, I would say probably the best first step is to simplify as much as you can in the beginning. Okay. So we could say simplify right away. Okay. So when you do that, it really draws our attention to this 24. The radical 6 is as simplified as could be, but this blue 24, on the other hand, hopefully we're recognizing, could be sort of broken down. So it's like 2, 12, 2, 6, 2, and 3. And there's this sort of pair of 2's, which would mean that one of these would get out of the radical, and then you'd have a 6 left over. So therefore, we're looking at 2 radical 6 times 2 radical 6. Okay, so then we could say step letter B is to multiply after that. And you're going to be multiplying the outside part and the radical part, right? So we could say outside part and radical part. Okay. Now, as a result of that, hopefully we're seeing that the 2 green outside parts would turn into a 4, and the 2 radical parts, you could think of it as 6 times 6 under there, and that would become a 36. So for my student watching, please remember that you want to kind of mix the outside with the outside and the radical part with the radical part. And then really, for part C, we could say simplify again if need be. Okay. Now, can we do that? Well, yes, because 36 is a perfect square. And I think my student watching understands that that would be 4 times 6, because the square root of 36 is indeed 6. And then we would have 24 there. Okay. So I really think that a step-by-step process like this would be really good for some of these, if not all of them. So let's find out what's up with this one. Can we simplify right away? Well, as far as the 3n, there's really nothing we could do here. Over here, we can simplify that. So let's kind of draw our attention to the red situation. We have 27 n to the 5th power. Let's focus on the 27 first, okay? So the 27, hopefully my student watching understands, that can indeed be broken down into 3 times 9, and then 3 times 3. And then for my student watching, she knows that this pair of 3's would imply that one of the 3's is about to get out. So we therefore know that the update at this point is that there would be a 3, and then there would be this poor green 3 left over, right? That poor green 3 is left over, and then we still have this n to the 5th power. Now, this n to the 5th power, in my opinion, is pretty tricky. It is the case that my student did a pretty good job with something like this, I think, when we were chatting. So what you could recognize when it comes to that is the fact that all of this could be rewritten, and that n to the 5th is secretly an n to the 4th times an extra n. And it's the case that all of that could be rewritten. And it is the case that that n to the 4th could be rewritten as n squared squared. And why am I doing that? The reason I'm doing that is because this blue parentheses is now being raised to the 2nd power, which means that this blue parentheses is about to get out. So we could say it's 3n, and then you have that blue n squared on the outside times this 3, right? This yellow 3 right here. And what's left on the inside? Well, what's left on the inside is that green 3 and the red n. Okay, so I feel like we just simplified right away. We simplified as much as we could over here. Step letter B, multiply the outside part and the radical part. Okay. Well, the outside part is just this. You have a radical part here and a radical part here. So the outside part is just that. And I think my student watching would agree that that could just be rewritten as 3n squared. And when it comes to multiplying the radical part, that would be, 9n squared. And then hopefully my student watching realizes that that is really just going to be this scenario, right? 3n squared. So it's this that gets out, and the next thing you know, you have 3n times that other 3n, and that's going to be a 9n squared. Okay, hopefully that makes sense. Okay, so we simplified again after that. Now, for my student who's watching, just know that I chose to just follow this step, which is to multiply the radical parts, 3n times 3n, and that gave us 9n squared. Now, you would have been able to catch that this is just going to be 3n times another 3n underneath the radical, just like this, and then therefore just realize, oh, it's just going to become a 3n. Okay, so hopefully that makes sense. Let's see over here if we were to use this step-by-step process, which I think is a decent one. Simplify right away if possible. Well, it is the case that this t could kind of get out. So let's just rewrite that part. So we have the first part, which we're kind of stuck with. The t is going to get out, and then we have that 14 there, right? Now, that's as simplified as could be. There are no perfect square factors here. That's as simplified as could be. So step letter B, multiply the outside part and the radical. So we are looking at 6t. Then you would have 7 times 14, which is 70 plus 28, which is 98. And then you still have that t from here, right? Now, step letter C, simplify again. So let's see, the 98, the blue 98, hopefully my student watching recognizes that could be split as 2 times, I guess that would be 45 plus 4, so that would be 49, and then that would be 7, right? And then you have your pair of 7s there. So a 7 is going to get out, so we're going to have a 6t times a 7. And then who's left on the inside? This poor green 2 along with the red t. Now at that point, you could, simplify, complete this step really, because we could simplify the outside now. Hopefully my student watching recognizes that that's just 42t. And then you have that radical 2t there. Okay, so once again, this step-by-step process seems to be working out decently for us. There might be some exceptions, but we're going to find out. Okay, looking at problem number 4, simplify right away. Well, I kind of like this. So we could sort of simplify this situation that's under the radical, because the reality is that 36 over 4, I mean, that's really just 9, right? And that's just a 1. And I think my student watching knows that there are sort of a string of 3 A's being multiplied across the top. There's only one A down here. So one of the A's here, one of the A's up here is going to cancel with the A down here. So that would result in this thing being canceled, and then you have that 2. Okay. Now, in case that's confusing, just remember there's another law that says a to the third over a to the first. You could just keep the base and subtract the exponents. 3 minus 1 would give you a 2. So what are we left with? We are left with this big clunky radical. We have literally just 9a squared right now, right? And step letter B, multiply the outside part and radical. Well, there is nothing to multiply. So step letter C, simplify again. Okay, cool. So we have 3a, right? because this blue a is being raised to the second power, and that green 9, the square root of that green 9 is really a 3. Cool. So this is where it gets kind of interesting because, let's see. Let me just group all this one moment. So I think problem number 5 might be the first time where we are breaking away a little bit from the protocol. Now, part of the protocol that I think I'd like to keep, though, is to simplify right away. I think you're always going to kind of want to do that, for sure. So, but what's different about this one is we have this radical that's like on the bottom, okay? Now, in reality, there's secretly a radical on the bottom here, but this is a little bit more like a radical over the whole thing. This is the first time where it's very clear that there's a radical on the bottom. And whenever that's the case, I'm going to say that step letter B, okay, for this situation, this is a special situation. Special. Not the best handwriting. So step letter B is to rationalize. And then I think probably to simplify again after that, we'll keep that in red actually. Simplify again after that. I think that'll probably always do it. Now, what do I mean by rationalize? Well, we have this situation, and mathematicians do not like it when there's a radical in the denominator. So what you do is you multiply the top and bottom by whatever it takes to get rid of the radical on the bottom. And it turns out that what it takes is to literally just multiply it by radical x. And I think we would agree that that's going to become radical 5x up top, and then down below it's just going to become x. Now, in case that's not clear as to why that happens, let's go off to the side and think about it. For my student watching, isn't it true that on the bottom we have radical x times radical x? Well, that's what we have here. And isn't it true that that's really just radical x squared? And isn't that just x? Okay, so that is why we have that x down here. And then step letter C is to simplify again, and there's nothing to simplify here, so we're good. Cool. Cool. Then we have this. Bringing the rules over to this one. And simplify right away. Okay, can we do that? Well, actually, yes, because that 12 up top is 2 times 6, and then that's 2 times 3, and you have that. So right away, we can call that 2 radical 3 over radical 15. Okay, step letter B, rationalize. Get rid of the radical on the bottom. Okay, so that means radical 15, radical 15. And next thing you know, down below, certainly it's 15. Up top, it would be 2 radical 45. Step letter C, simplify again. Can you do that? Well, yes, you can, because we have that blue 45. I think we would agree that that could be split into 3 times 15. And then 3 times 5, there is a pair right there. So that means a 3 is about to get out. So we have 2 times 3 times radical 5 over 15. And then that is going to be 6 radical 5 over 15. Now, believe it or not, we're not done with step letter C. We're still simplifying, because even after having done that, now we have a 6 over 15. 6 is divisible by 3, and 15 is divisible by 3. So that 6 divided by 3 is 2. That 15 divided by 3 is 5. So this is going to be 2 radical 5 all over 5. Hopefully that makes sense. That is the answer to that one. Let's put my 3-step process to the test over here. Simplify right away. Can that be done? Yes, because that 24 can turn into a 2 times 12, 2 times 6, and a 2 times 3. We have this pair of 2's right there. So it's going to become a 2 radical 6 over that radical 3x. Step letter B, rationalize. Okay, cool. Radical 3x radical 3x. Next thing you know, you have what? 2 times radical 18x all over literally just 3x. And step letter C, simplify again. It is the case that that could be 2 radical, 18, right? That becomes 2, 9, and then 3, and then 3. So we have a pair of 3s. So actually, I'll just erase this really quick. Hopefully my student watching recognizes that because there's that pair of 3, there's going to be a 3 that gets out over here. So we have 2 times 3, and then who's left? 2x is left, and then we have a 3x. Now, this is going to become a 6 soon. However, because we want to simplify again, we could just kind of capitalize on this moment where we have a 2 times 3, and there's a 3 there. So let's just kind of cancel these right away. You can get away with that. And then we have 2 radical 2x all over x, and then you're done. Okay. So, yeah, let's steal this. And is this going to come up again? Well, actually, let's bring it over here, right? We don't want to skip anything, do we? Okay. Why is this like deja vu? I feel like I did this. Okay. So simplify right away. Can you do that? No. Step letter B, rationalize. Can we do that? Yes. So that's radical 3y, radical 3y. Next thing you know, you have 18y all over 3y. And then that is going to become 3 radical 2y over 3y. And then these will cancel. And the next thing you know, you have radical 2y over y. Okay. So I kind of just cut to the chase there. Simplify right away. There was nothing to simplify. Rationalize. Okay, we did that. And then simplify again after rationalizing. Part of simplifying again was not only turning the radical 18y into 3 radical 2y, but part of simplifying again was to actually cancel these 3's as well. Okay. For these, when you're adding and subtracting, I think maybe step letter A is to simplify as much as you can, and then step letter B, add or subtract. Or we could say, I'm going to say something else. I'm going to say simplify as much as you can, and then I'm going to say multiply, divide, add, or subtract. Okay. In a way, it's just PEMDAS, really. And will we have to simplify after that? I don't know. We're going to see. Step letter A is to simplify right away, though. So we have 75, and then we have 3 times 25, and then we have 5. And then 5, so we have a pair there. So I think my student watching agrees that that's going to become 5 radical 3. And then we will be adding, right? So we have like terms. For my student watching, just remember this is much like x plus 5x. What would you do if it was x plus 5x? I think you would agree it would become 6x. And for the exact same reason, it's going to become 6 radical 3. All right. Now, once again, this is what we do when we add radicals, right? Very different than what you do when you multiply radicals. Okay. I think, yeah. Let's use our protocol. Simplify 80 would become 2 times 40, 2 times 20, 2 times 10, and then 2 times 5. We have a pair here, a pair here. So that means 2 2s are getting out, which is really like saying a 4 is getting out. So that's really 4 radical 5. And then we have 8 radical 5. Now, for my student watching, when you see addition, it's kind of like 8x plus 4x, and that would be like 12x, right? But it's really 12 radical 5. Okay. Using our protocol, simplify first, then multiply, divide, add, or subtract after that. So simplifying, we have 150 and we have 20, or 54 rather. 54, so 150 would become 2 times 75, and that's really 3 times 25, and that's really 5 times 5. So we have a pair there. I'm just going to keep going with this, though. We have 2 times, okay, 25 plus 2. That's 27. That's clearly 3 times 9. We have 3 times 3, and we have a pair here. Okay, so I think we all agree that the radical 150 is going to become 5 radical 6 minus 2 times something. 2 times one of these green 3's there, so it's 2 times 3. And then who's left there? That's going to be a 6 under there. Cleaning it up, that's 5 radical 6 minus 6 radical 6. And that's kind of like 5x minus 6x. And I think my student watching agrees that would be negative x, also known as negative radical 6 in this case. Okay. Over here, using the protocol of simplifying, multiply, divide, add, subtract, which is what you want to do with these. So I'll just kind of barrel through this. This is going to become 5 times an extra 5 radical 2 minus 3 times an extra 3 radical 2. Cleaning that up, that's 25 radical 2 minus 9 radical 2. For my student watching, feel free to pause it if you feel like that would be helpful, and try it yourself, but I'm pretty sure I'm right about that. So it's kind of like 25x minus 9x, so that will be 16x, aka 16 radical 2 in that case. Okay, so simplifying in this case would actually mean distributing. Okay, simplifying would mean to turn this into sort of an addition subtraction, a purely addition and subtraction situation. And this sort of multiplication setup is not as simplified as could be. So we will be distributing that radical 5 in there, and that radical 5 times radical 2 is radical 10, and radical 5 times 3 is plus 3 radical 5. And then multiply, divide, add, subtract. Well, there's really nothing else to do there. Okay. So we're actually done with that one, believe it or not. And for my student watching, just think about it. Is there anything you can do to combine these? No, because like radical 10 is as simplified as could be. So you'll never be able to turn this radical into a radical 5 with something on the outside. So you just can't combine them. Okay. So that's that page. Okay. Same kind of deal, right? We're looking at, my directions were simplify first, right? So always simplify first. Okay. Now, what do I mean by that? Well, that 12, radical 12, right? Couldn't this be rewritten as 2 radical 3 plus 4? I feel like that could. So then distribute after that. Okay. So that would be 2 times 3 plus 4 radical 3. Now, for my student watching, why did that become 2 times 3? Well, the 2 is just this blue 2, right? And then you had a radical 3, a green radical 3 times another green radical 3, and that just becomes a 3. So I invite you to just think about that once again. We sort of alluded to that before in this video. Okay, so just think about that. But 2 times 3 is 6, of course. So we have this and we have that. Okay, and that is as far as we can go. There's nothing we can do with that. We have a 6 plus 4 radical 3. It's kind of like a 6 plus a 4x, you just can't combine those. Those are not quote unquote like terms. Looking at this, obviously, simplifying first is a good idea. Now, there's nothing, or is there something we can simplify? Yes. We want to simplify it first. And that radical 8, that 8 becomes a 2 times a 4, 2, 2. So we have a pair of 2's. So that radical 8 is going to become 2, radical 2 on the outside. And I would do that first. And then we are distributing. So we have 2 times radical 2 radical 2 times radical 3. That's 2 radical 6 because the yellow radical parts are going to multiply together. Notice how the 2 that's on the outside remains on the outside. The 2 radical 2 times 6. Well, this is almost like the opposite because that red 3 is not inside a radical. Similarly, this red 2 is not inside a radical. So the red things are going to get multiplied together. So that becomes that, right? And then we have the radical 2 right there. And I'm kind of using a lot of color coding here. So let me just write it in a normal fashion. So hopefully we see that that's actually as far as we can go. It seems like maybe you should be able to do something with that, but you can't because that's a radical 2, that's a radical 6. That cannot be simplified any further. This is kind of like a 6x, and this is kind of like a 2y, and you can't combine those. Okay. This one, simplifying right away. That's as simplified as could be. That's as simplified as could be. There's really nothing else we can do other than distribute. So the blue 5 or the blue 5 stays on the outside, but the radical parts get multiplied to each other. That's going to become a 28, and that's minus 15 radical 2. And then look at it and ask yourself, can that simplify? Well, yes, that could simplify because 28 is really 2 times 14, which is really 2 times 7. And then we have that. And then we have 5 times 2. And then we have this radical 7 minus 15 radical 2. We have 10 radical 7 minus 15 radical 2. And I think we are good there because that's kind of like 10x minus 15y. There's really nothing you can do with that. Okay, my student watching did a good job with FOIL. Whenever you have a binomial times another binomial, that's a good idea to FOIL. So first times first, I think we agree would give us 15, radical 15. Outer times outer would give us a positive 2 radical 5. Inner times inner would be a negative radical 3. And last times last would be a negative 2. And then you can just look at it. Is that as simplified as could be? Yes. Is that as simplified as could be? Yes. Is that as simplified as could be? Yes. And of course that is. Are there any so-called like terms, right? No. I mean, that cannot combine with radical 5. They're not the same, right? So we are actually stuck with that situation. Okay, is it as simplified as could be in the beginning? Yes, it is. Okay, time for FOIL. So first times first would be 10 radical 6. Notice how the blue outside parts got multiplied together, became a 10, and the green inside parts became that green 6. Outer times outer would give us negative 10 radical 2. Inner times inner would give us plus 2 radical 3. Last times last would be negative 2. Similarly, we are stuck with this. The radicals do not match. There's nothing else we can do. We are kind of stuck with that. There's a 2 here, which implies FOIL. Now, there is a fancy pattern you could memorize, but if you're not up for that, you can just rewrite it as follows and realize that that is also a FOIL. First times first gives you a 3. For my student watching, feel free to ponder that. I've been kind of harping on that concept for a little while, but radical 3 times radical 3 is literally just 3. Outer times outer would be negative 4 radical 3. Inner times inner would be also negative 4 radical 3. And then last times last would be a positive 16. This time you can simplify because those happen to be like terms. And also, by the way, these happen to be like terms. So the 3 plus 16 is 19. And the negative 4 radical 3 minus another 4 radical 3 is just this. And then we're good with that. Okay. Same deal, right? Same deal. This is as simplified as could be, right? First times first is 16 times 7. We'll worry about that later. For my student watching, the red 4s became the red 16. The blue radical 7s literally just became 7. For my student watching, just ponder that as much as you want. Then we have plus 4 radical 14. That's a result of the O in FOIL, right? The 4 radical 7 times radical 2 becomes that. The I in FOIL would give us 4 radical 14, and the L in FOIL would give us a 2. 16 times 77 rather is 70 plus 42, which is 112. It's the case that these would combine. That would become plus 8 radical 14. And then, of course, we have this plus 2. And then simplifying further, because those are like terms, we have 114 plus 8 radical 14. Hopefully that makes sense moving forward. This right here, also FOIL, I'll just cut to the chase. That's 4 times 3. That will be 4 radical 3 minus 4 radical 3 minus 4. Now, this is sort of something minus something, and that same first thing plus the same second thing. So this is sort of a difference between two squares pattern that they're throwing at us, but just foiling it is a good idea. So this would be 12 plus, well, actually, these would cancel, right? And then 12 minus 4, that's 8. Okay, so that's that. Similar pattern, A plus B times A minus B. So the teacher's kind of warming everyone up for this pattern because this pattern is going to show up relatively soon. I'll just cut to the chase. So for my student watching, anytime you see that it's like something plus something and that same thing minus the same second thing, that is just going to become a squared minus b squared. So in other words, this is just going to become something squared minus something squared, namely the red 2 squared and the blue guy squared. Okay, so that's 4 radical 5 squared. The red 2 squared is, of course, 4. Now, this becomes minus 16 times 5. For my student watching, just know that the 4 became a squared, that became a 16, and the radical 5 became a squared, and that is a 5. So 16 times 5 is 80, so it's going to be 4 minus 80, and that is negative 76. Okay, so the moral of the story for my student watching is this kind of pattern is going to show up, and it would actually benefit you to just recognize that a plus b times a minus b is really a squared minus b squared. Now, you might be wondering, could I just FOIL it? Yes, you could totally just FOIL it. In fact, that's what we did, I think, on the previous problem. That was an a minus b times a plus b, which is really the same thing. We did FOIL that, and it worked out fine. Okay, but as you can see, this whole parentheses squared minus parentheses squared, that's actually pretty fast. It's faster than foiling it. So, okay. Now, this is why the teacher was warming everyone up for it, because these are such that you want to get rid of the radical on the bottom, and the way to do it is to multiply the bottom by the conjugate. And the conjugate is a special binomial, and this is what you do. You have a binomial on the bottom. Conjugate is a special binomial such that it's the same thing, only the opposite operation in the middle. So up top, I think my student watching agrees that that 1 is just going to distribute there. So it's going to become radical 3 minus 2. Now on the bottom, I actually would encourage my student to definitely do that pattern, which is something squared minus something squared, namely radical 3 in there, namely 2 in there, because that's actually going to make it easier. Now up top we have this. Now on the bottom, radical 3 squared is literally just 3 minus 4. And then hopefully my student watching recognizes that that is very simply this. And, there's kind of you could leave it like that. The teacher might be cool with that. It is the case that anytime you take a number and divide it by -1, it just changes the sign. So this could be rewritten as that. Okay, because the -2 becomes a +2, and the positive radical 3 becomes a negative radical 3. Now, if that's confusing for my student watching, don't worry about it. I have a feeling the teacher might be cool with this. Maybe just double check. Okay, so that's that. Um, this one here, same deal, just multiply the top and bottom by the conjugate. So we have radical 5 plus radical 2, radical 5 plus radical 2. Up top, of course, distributing, right? So we have a 3 radical 5 plus a 3 radical 2 all over something squared minus something squared. And what goes inside? Well, that is a radical 5. That is a radical 2. Up top, of course, 3 radical 5 plus 3 radical 2. Down below, we have a 5 minus 2, aka 3 down there. And then up top, it's the same thing. So, this one though, yeah, the teacher's being sneaky because at the tail end, now I have experience for my student watching, I have experience, so I'm able to kind of catch this sometimes. I do make mistakes, of course, but I'm able to catch that there is sort of this GCF of 3 up top. Now, what that means is that you could hypothetically factor out that 3 up top. I'd actually be surprised if your teacher didn't want you to do that, because this top, you could take out the 3 up top. Let's keep the bottom 3 yellow. Okay. So with regards to the blue 3s, you could factor out the blue 3. And what's left in here is radical 5 plus radical 2. And then what your teacher probably wants is in this moment, because this is multiplication, this is just some number times some other number. Whenever there's multiplication, that's when you can do this cancellation. All right, and then that just becomes this. So that's that. Looking at this right here, conjugate, of course, radical 2 minus 4, radical 2 minus 4. Distributing, we have radical 14 minus 4 radical 7. It's going to be something squared minus something squared, aka radical 2, and then 4. Up top, is there anything we could do? No, we're kind of stuck with that, aren't we? And then on the bottom, of course, it's 2 minus 16. And that is going to be the same top all over negative 14. Is there anything we can do with that? I don't think so, because that can't be simplified any further. That can't be simplified any further, and there's really no greatest common factor here that we could factor out and then cancel with the bottom. The only thing you say is that sometimes, like, the official answer will have this green negative symbol sort of off to the side of the fraction. But I think that really doesn't matter. So that's that. Okay. Now we're getting into some trigonometry stuff. Let's remind ourselves of SOHCAHTOA. And we have this sort of right triangle where that's a theta. This is the opposite side. This is the adjacent side. And this is the hypotenuse. Now, SOHCAHTOA reminds us that sine of an angle is opposite is we could say O over H. O over H. Cosine of an angle is A over H, and tan of an angle is O over H. Now the O stands for opposite, right? The H stands for hypotenuse. Although I screwed up, didn't I? Some of y'all may have caught that. That's an A. And speaking of A, the A stands for adjacent. Okay, great. So yeah, that's going to be helpful. Notice for my student watching, the hypotenuse, once again, is the longest side of the right triangle, and it's always across from the 90 degrees. Okay, looking at problem number 28. Triangle has a hypotenuse of 8. Cool. Drawing it 8. Yay. The leg adjacent to the angle is 4. Okay, we'll call this the angle. So that'll be 4. Draw the triangle and find the length of the opposite leg using the Pythagorean theorem. Okay, yeah. So that's the other concept, which is a squared plus b squared equals c squared. And that's the case when we call the hypotenuse c. We call one of the legs a and the other one b. Okay, so we want to find the length of this leg right here. So hopefully my student watching recognizes that we could literally just call that b right now. And therefore, it would be 8 squared, or pardon me, it would be 4 squared plus b squared equals 8 squared. Okay, what is that? 16 plus b squared equals 64. B squared equals 64 minus 16. That would be, I guess, 48? I think so. 14 minus 6 is 8. And then 5, yeah, I guess so. So then at that point, your teacher is expecting you to know that you still haven't solved for b yet, so you have to do this thing where you radical both sides. Okay, you square root both sides. And in doing so, now the b will be by itself because that square root symbol cancels the exponent of 2. And this can be simplified because 48 turns into 2 times 24, which is really 2 times 12, which is really 2 times 6, which is really 2 times 3. We have a pair of 2's, we have a pair of 2's. So that means 2 2's get out, giving us a 4 radical 3. Okay, so we satisfied finding the length of the opposite leg using the Pythagorean theorem. It is a strange number, but that is the answer. It's 4 radical 3. Okay. Find the sine, cosine, and tangent. Okay, well, this really shouldn't be too hard when you have your triangle labeled fully, which we do, right? The hypotenuse is labeled. It's an 8 units long. This leg is labeled 4 units long, and this is 4 radical 3 units long. Now, the only thing I'll say is maybe it would help us to remind us that this is the hypotenuse, this is the adjacent side, and this is the opposite side, okay? Now, for my student watching, I think probably by now knowing that this is the hypotenuse is pretty clear. What might be less obvious is the opposite. Well, just remember, the angle is in the little nook in the corner, and you think of the triangle as like a lake, and who's on the opposite side of the lake? This side, B, is on the opposite side of the lake, so we call that the opposite side. Adjacent, you could think of next door neighbor, like right next to you, but it's not the hypotenuse. Okay, so therefore, the sine of the angle, right? Find sine, cosine, and tangent of this angle, which we're calling theta. Okay. And they kind of, alluded to some angle. Now notice we don't know what the measure of that angle is, right? We have no idea. It might be 30 degrees, it might be 40 degrees, I don't know. But it doesn't matter, right? Because when they ask for the sine, cosine, and tangent, they're just asking for these ratios of side lengths. So opposite over hypotenuse, I think we would agree that is equal to 4 radical 3 over 8. And since 4 is divisible by 4 and 8 is divisible by 4, 4 divided by 4 is 1, 8 divided by 4 is 2. So that would just become radical 3 over 2. Adjacent over hypotenuse, that would be 4 over 8, and that reduces to 1/2, I'm sure everyone agrees. Tan is opposite over adjacent, so that is 4 radical 3 over 4. Now, these would cancel, and that would leave us with literally just radical 3. Hopefully that makes sense. Oh, yeah, they wanted all three. Okay, good. We did that. Let's keep this. I just feel like this is going to come up again. But let's erase stuff. We're going to erase this. And maybe this will be our template moving forward. So I guess this is a similar type of question. Triangle has a hypotenuse of 2. Yeah, cool. So I'll just draw that. 2. The leg opposite of the angle, let's call this the angle, is radical 2. Draw a triangle and find the length of the adjacent leg. Okay, so we'll just call that A. Due to the Pythagorean theorem, I think we all understand that that is going to be a squared plus radical 2 squared equals 2 squared. A squared is just a squared. Radical 2 squared is just 2. Okay, ponder that if need be for my student watching. 2 squared is just 4. A squared is therefore going to be equal to 2 because we can subtract 2 from both sides. And hopefully my student watching recognizes that this is the moment where you would indeed take the square root of both sides, and that would be a equals radical 2. Okay, so therefore this a is equal to radical 2. Now it's also the case, now by the way, for my student watching, feel free to label it, if you have to, opposite, hypotenuse, and this is the adjacent. Now that's all in relation to this angle. We already decided that this is going to be where our angle is, right? We just draw it. And then what's the opposite side to this particular angle? It's this. What's the adjacent side to this particular angle? It's this side. Okay. So sine, cosine, tangent, let's remember. SOHCAHTOA, right? I guess I didn't need to write that because it's right here. So cool. Opposite over adjacent is radical 2. Opposite over hypotenuse, rather, is radical 2 over 2. That cannot be simplified. Adjacent over hypotenuse, also radical 2 over 2. And then finally, opposite over adjacent is radical 2 over radical 2. Now, for my student watching, anytime you have a number divided by itself, that's literally just 1. So that's 1. Okay. So for my student watching, just remember, the presence of all these radicals is crazy and maybe a little distracting, and for some it might be intimidating, but just think about the big picture concepts. The big picture is, of course, SOHCAHTOA, opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. It's really not that big of a deal. And the other concept, the only other concept so far, is the Pythagorean theorem, which we already discussed. You just need to remember that the so-called C is the hypotenuse. That's important. Okay. The hypotenuse is not one of these two. It's this one. And that's really all you need to know at this point for the freaking trig stuff, I think. Yeah, more of the same. I'll just barrel through this one. We will draw it in much the same way. The hypotenuse is this. The leg adjacent to the angle. Okay, let's make this the angle. The leg adjacent is 10. We will make that B again. In fact, I'll keep it blue because that's what it was before. Draw the triangle, find the length of the opposite leg using the Pythagorean theorem. Okay, cool. 10 squared plus B squared equals, careful, whole quantity squared. Okay, there's a 10 in there. Okay, so that's 100 plus b squared. Now, when you square a product like this is like a clump of multiplication being squared. That exponent of 2 gets applied to the 10, and the exponent of 2 gets applied to the 2. Now, when we apply the exponent of 2 to the green 10, that's going to become 100. When we apply the exponent to the radical 2, that's going to become just 2. Ponder that if need be. Then we have 200, 100 plus b squared. Subtracting 100 from both sides gives us 100. Square rooting both sides gives us 10. So it turns out that b is equal to 10. So ka toa, right? Sine of an angle is going to be something. Cosine of the angle is going to be something. Tan of the angle is going to be something. The sine of the angle is 10 over 10 radical 2. That could be simplified because these would turn into a 1, and then you would be left with a 1 over radical 2. Now, this is the most annoying one so far because the teacher probably wants you to catch that even though we did this correctly, it's the case that that needs to be rationalized. So on the bottom, it's just going to become a 2, but on the top, it's going to become a radical 2. Okay, the cosine is adjacent over hypotenuse. So that's going to be 10 over 10 radical 2. Well, the good news is that we just kind of processed that. We already know that that's going to turn into what we just said, which is this. And then finally, tan of the angle is equal to opposite over adjacent, which is 10 over 10. And that is just a 1. Pretty sure I did that right. Yeah, that is exactly. Okay, so great. Problem number 52. A 52-degree has an adjacent leg 8 inches long. How long is the hypotenuse? Okay, so I guess it's a right triangle. Right? That's what they're talking about probably, right? So we have 52 here. The adjacent leg is 8. Okay, remember that's the op. That's the adjacent. And this is the hypotenuse, right? So the adjacent leg is 8 inches. How long is the hypotenuse? Yeah. So this is a leap in complexity, okay? Step number 1, draw the picture. Okay, definitely draw the picture. Step number 2, get clear on the cast of characters. Step number 3, choose your trig function. Step 4, write your equation. And step 5 is going to be solve the equation. Well, step number 1, we already do. We drew the picture. Step number 2, get clear on the cast of characters involved. Well, really, they just want to know the hypotenuse, and we already have the adjacent. So let's actually literally ignore the opposite, okay? So we just got clear on the cast of characters that happen to be involved in this particular problem. The only characters we need to deal with are the adjacent and the hypotenuse. Step number 3, choose your trig function. Now, what do I mean by that? I mean choose between sine, which is so, cosine, which is ka, and toa, which is, tan, right? So choose between these. How do you choose between these? Well, it depends on the characters. What were the characters? We have an angle, we have adjacent, We have a hypotenuse. We have an A and we have an H. We have an A. We have an H. So that is a cosine situation. So we are choosing cosine. Step number 4, write the equation. Okay, well, the equation is that cosine of an angle, in this case it's 52, is equal to adjacent over hypotenuse. So that would be 8 over h. Okay. Now, step number 5, you have to solve that. Okay. So I'm going to cut to the chase for my student watching. For step number 5, we want to solve that anytime the variable is in the denominator, you can just swap it with this guy over here. So that is just going to become h equals 8 over cosine of 52. Now, there's a justification for that, but I actually would like my student to remember that trick. I call it the swapperino. Okay. Anytime you have a variable down here, and it's just a single fraction and some monomial over here, you can just swap these. Now, this is something you'd have to plug into your calculator, okay? So 8 over cosine 52 is really 8 over 0.66 in the calculator, and that turns into, and that's really approximately, and that turns into approximately 12.12, okay? So if you have a triangle and a right triangle and this is 8 and that's 52, then we know for a fact that that has to be 12. Okay. Now that could be really overwhelming, but I think really it just comes down to following these steps and not getting overwhelmed. I mean, there's that moment when you're solving the equation where you have to remember you can just swap the h with this thing, you know. But this is sort of the hard case. Most of the equations that you'll be setting up for yourself are actually pretty easy. So let's put my 5-step process to the test with problem number 32. Okay, draw it first. Okay, here we go. Drawing it. The hypotenuse is 15 millimeters. How long is the side adjacent to a 15-degree angle? Okay, let's put the angle here, as usual. And we want to know how long is this adjacent side, right? Okay, well, we just successfully drew the triangle. Step number 2, get clear on the cast of characters. It is the adjacent and the hypotenuse. Step number 3, pick your trig function. Is it going to be so? Is it going to be ka? Or is it going to be toa? Well, since it's the adjacent and the hypotenuse, I mean, I feel like it's the same characters that we were just dealing with up here. So that's going to be cosine. Step number 4, write the equation. Okay, cool. Cosine of 15 is equal to adjacent, in this case it's A because we called it A, over the hypotenuse. Now this one we will not need the swapperino. You only need the swapperino when the variable's on the bottom and you swap it. The variable's on the top here, so all we have to do is multiply both sides by 15 right now. Okay, and this 15 is this green 15 for the record. And the reason we multiply both sides by 15 is now these will cancel. And then it's going to be A equals literally 15 times cosine of 15. Now, for my student watching, just know that this is its own number. And in fact, I'm going to put parentheses around that. And this is cosine. Okay. So this is its own number, cosine of 15. That's something you could literally plug into your calculator, and it's going to give you some decimal. Okay. And what we're doing is we're multiplying this number times 15. Now, typically when you're multiplying a trig function times a number, you put the number out front. So it's very clear that it's going to be this 15 times this, whatever this number is. Okay. So when you plug that in your calculator, it's going to be 15. I'm literally just going to use a calculator. I'm going to go 15 times cosine of 15 right now. And that turns out to be 14.49. Okay. So what we learned is that if that's 15 degrees in this little nook here, and the hypotenuse is 15, it turns out that this side has to be 14.49. Now for my student watching, once again, do not worry, just follow the steps. That's it. All right, let's put the steps to the test again. 60-degree angle, opposite leg, blah, blah, blah. Okay, cool. Step 1, draw. 60-degree angle, 60 degrees. Notice how I'm always choosing to put the angle down here. Why not? Opposite leg. Ooh, opposite. Okay, what's the opposite? That's this, because it's all the way across the water. 10. How long is the hypotenuse? Okay, h. We need to find. Okay, step number 1 is accomplished. We drew the triangle. Step number 2, who is the cast of characters? Well, that is the opposite and the hypotenuse. Step number 3, which trig function do you pick? Well, the one that has to do with the opposite and the hypotenuse. It's sine, because sine has to do with OH, opposite hypotenuse. Cool. Step number 4, write the equation. Okay, well, it's going to be a sine, right? It's sine of 60 equals opposite over hypotenuse. Uh-oh, we got a swapperino alert. See that blue H? That blue H is going to swap with the sine. So the blue H is here, and then we have 10 over sine 60. That is something you could just throw into your calculator. I'm going to throw the whole thing into the calculator right now, and that's going to become 11.55. Okay. So what we just learned is that if that's 60 degrees and this side is 10, then we know for a fact, no matter what, that this hypotenuse is going to be 11.55 long. Okay, so that's that. Okay, for each triangle, find all 3 angles to the nearest 10. Okay, so already I can see this is going to require 2 additional concepts because what makes these problems different is now they're asking us to find the angles. Notice how in the previous problems they gave us the angle and they asked us to find the side length, but now they want us to find the angles. Now, one concept that's going to be useful is the fact that all the angles, let's call this angle X, this angle Y, and this angle Z, when you add these in a triangle, they will always add up to 180. Now that ends up being very useful information because if that's 30 and that's 40, well, you know that that has to be 110, okay? Because 30 plus 40 is 70, and then we need to get up to 180, right? So 180 minus 70 is 110, right? So that is going to turn out to be very useful. Now, another thing that's going to be useful is sometimes they're going to ask you for the angle, like let's say the angle we're calling theta. And we don't know much about theta at all, right? We don't know what the angle is, but we do know that tan of that angle happens to be 3 over 5. Well, there's a special function in the calculator that says that you can find out what the angle is by taking what is called the inverse tangent of 3 over 5, okay? And that is a function in the calculator. Now, it is good to kind of get to sort of write this down first and then pause, take a deep breath and be like, okay, I remember the teacher said when I'm trying to find the angle, because I don't know the angle, I can just do the inverse tan. And the answer will be this in the calculator. Okay, so those are 2 extra concepts we need right now. The fact that all the angles add up to 180 in a triangle, and the fact that if the unknown happens to be the angle, well, then you can hit it with the inverse trig function. And this would apply to inverse sine and inverse cosine as well. Okay, I think this is probably still going to be useful, though, believe it or not. So let's find out. Okay. Shrink that down. And the hypotenuse is 10 feet long, the adjacent side. Okay, so I'm just going to literally draw the situation, which is step number one, right? So we have 10, and the adjacent side is 5, right? So remember, adjacent is the side that's next door to the angle. So let's just find theta first. That's sort of our goal at this point. Okay, so who's the cast of characters? The cast of characters is adjacent and hypotenuse, right? So which trig function are we going to use? The one that has to do with adjacent and hypotenuse, that's cosine. Step number 4, write the equation. Okay, cosine of whatever the angle is equal to 5 over 10. We could also say that cosine of the angle is equal to 1/2, right? So we just satisfied step number 4. We wrote the equation, simple as that. Step number 5, solve. Okay, we will solve the equation, but now we're solving for the angle. And anytime you're trying to find an angle, you can always just do the inverse cosine, okay, of that number. And that is going to be, in your calculator, 60 degrees, okay. So we can actually update the situation to reflect the fact that this is 60 degrees, right? Now, we want to find all 3 angles. That is what the directions called for. See the green thing? Find all 3. Well, we have 2 of them, don't we? We know that that's 60, and we know that that's 90. So due to the fact that when you add all of it up, it should be 180, doesn't that mean that this one needs to be 30 degrees? Okay, so for my student watching, ponder that if need be, but that is the case because all the angles have to add up to 180. Okay, I feel good about that one. Let's look at this one. And drawing the triangle. So the good news is for my student watching, that 5-step process that worked on the last batch of problems also works on this. So the opposite side is 20, the adjacent side, so we'll call that the angle. The adjacent side is 15. Okay. Step number 1, draw the triangle. Well, we just did it. Step number 2, cast of characters. This is the opposite side, and this is the adjacent side. Step number 3, identify which trig function you want to use. Well, it has to do with the cast of characters. We have the opposite side, we have the adjacent side. So that's TOA, right? Opposite, adjacent, opposite, adjacent. So that's tan, right? Step number 4, write the equation. Okay, tan of whatever that angle is equal to opposite over adjacent, also known as 20 over 15. And we could also say that tan of that angle is equal to 4 over 3. Okay, solve the equation. That's step number 5. Okay, yeah, the angle has to equal the inverse tan of 4 over 3, right? And that's for the calculator. The inverse tan of 4 over 3 is approximately 53.13 degrees. I'm kind of ignoring this, and I shouldn't. Okay, so I'm going to not ignore that. We're rounding it to the nearest tenth, so that's really 53.1 degrees. Okay, so if that is the case, then this triangle really has that there. And the way we could represent that is by saying that's 53.1, yay. So then we want to find the other angle because we already know that's 90. We know that the blue one is 53.1, but now what's this one? Okay. Now, for my student watching, just know there's a cool little trick. Okay. You could be like, this plus that plus x equals 180, and then solve that, right? Because it is true. This angle plus this angle plus this angle, they all add up to 180, no question. But if you want to just know what this one is really quick, I'll just tell you. Just subtract this from 90. Okay. Be like 90 minus 53.1, and that will be the answer. Okay. So that's a little trick. So when I say in my calculator, 90 minus 53.1, that is going to be 36.9. Now, why does that make sense? Because these two have to add up to 90. Because 90 plus this 90 equals 180. I'll let you ponder that. So we satisfied the directions for that one. Okay, and finally, I would imagine this is the same. The hypotenuse is 6 inches long. Okay, yeah, let's just draw it. Hypotenuse is 6, opposite side is 3. Here's the angle. We drew it. That's step number 1. Step number 2, cast of characters. This is the opposite. In fact, they literally tell you it's the opposite of hypotenuse, right? That's the cast of characters. So for my student watching, if you're ever unclear about these so-called cast of characters, they're telling you, right? So pick the trig function that you need. It's either so, ka, or toa. Well, it's the one that has to do with opposite and hypotenuse. I think we agree it's sine, right? Step number 4, write the equation. Okay, cool. Sine of theta equals opposite over hypotenuse, aka 3 over 6. Now, let's be very clear. That is 1/2. Okay. We just accomplished step number 4, which is to write the equation. Step number 5, which is to solve. Well, of course, it's an inverse trig because we're trying to find the angle. So whenever you're trying to find the angle, that's what you do. So you throw that in your calculator, and that would give you 30 degrees. Okay, so that's nice. Let's update the triangle. This is 30. Now, if we use my little trick, if we want to know what this is, just subtract 30 from 90. So this has to be 60. And for my student watching, doesn't that make sense? 60 plus 30 is 90, and then 90 plus this 90 is 180. Okay? I do believe we satisfy the directions there. Anyway, this is sort of a late night video. Hopefully that makes sense. That is a lot of information. For my student watching, after sort of watching my explanations, I would just pick like the ones that are the most challenging and just try to do those, okay, yourself, without looking at the answer, and then check the answer on the video. Anyway, hopefully it was helpful to not only my student, but others as well, and I will talk to you later. Bye.